Okay, so we are live, audio and video is up, and this is our last lecture before the exam review. So we have our exam review on Friday, and today is our last topic of the semester. We're going to talk about tributary area. This is a topic I've usually reserved for the design courses, but I thought that given how this semester is going, we're coming back for 1 week. What do I want to cover this week that's easy to understand but very practical and employs the stuff that we've used this semester? And I thought tributary area would be a good topic to close everything out, because I do think it kind of puts a nice bow on the course as a whole. Up until now, if you were to ask somebody like, well, what did you learn from this class? It's like, well, we know that there's these beams and there's triangles and circles at the end of the beam, so we put these little arrows on them and we can draw these diagrams and do these integrals. But what I kind of want to do is take all that and say, well, how do you apply that in real life? You might see here on the board, I've got this 3D frame that I drew, and I kind of want to talk about how we would take the tools and the models that we've discussed this semester and how you would apply it in a real life scenario. And so that's kind of what I wanted to close the topic on, or the class on today. Just so you know, on the homework schedule, homework 8.3, it's still being graded, but I went ahead and posted the solution. Homework 9.1 is due today. And homework 9.2 is going to be assigned today. And remember, that one has no late submissions because I'm turning the solution on right when it's due. So, make sure you get that in, because I want you all to have that solution for the final. For the other remaining tasks, I did want to show you something. So there's two bonus assignments. There's the course eval and the CLO survey. For the course eval, I checked on Blackboard this morning and on my eval, on my MU for me, and what I saw was that there's 11 students that have done the survey, but only 9 of you have uploaded the screenshot. So a couple of you have done the survey, and I don't know that you've done it, and so you're missing out on those bonus points. Again, you can say I'm the the worst professor ever. Just let me know that you do that survey, and you'll get bonus homework points. As for the CLO survey, it looks like, and there was one student that even commented on this. I don't know who, but I have 11 people that have completed the survey and 10 people have uploaded their screenshot. And I think what happened is one student actually accidentally did it twice. And they even put that on their comment that they might have done it twice. So just be careful on the CLO survey not to do that twice. But again, those are pretty much free homework points. So if you haven't done that, make sure and do that between now and Friday. All right, let's talk about today's topic, which is tributary area, and really discussing this concept of system loading. So I mean, up until now, we've discussed like really a wide variety of structural analysis problems, and we've taken beams and frames and trusses, and we put all sorts of loads on them, and we've looked at the reactions, the internal forces, we've looked at deflections, we've looked at what happens if the loads move. I mean, we've done a lot in here, but a lot of our problems have been restricted to these mathematical models. Like if you remember, one of the things I said at the very beginning of the semester was we don't really analyze structures in this class. We analyze these mathematical models that represent structures. Well, I think that we've, beaten that topic into oblivion. In other words, like I think handling those models was really sort of the main focus of this class. But what I want to talk about today, and again, you'll see how this puts a bow on this, is how do we take those mathematical models and apply them in a real world scenario? So, if I have this frame, how do I take this frame and turn it into a simply supported beam with a uniformly distributed load? Because once I do that, the next step is, okay, now I have a model I can analyze. I can determine the shears on that beam, the moments on that beam, the deflections on that beam. And then once I've got that, I can go, okay, what beam do I need to use in order to safely resist those loads? And that's design. So, for those of you who've elected to take steel design next semester, that's kind of where we're going to go from there. Is, okay, you know how to do the analysis. Now, how do you take those, forces from a truss analysis, or those deflections from a beam, or what have you, and how do you take that and turn it into a real structure? Here's the structure with this many bolts and this many inches of weld, and this is the section that we're going to use, and so on and so forth. So I kind of want to talk about that. Now, what we need, the way that we need to talk about that from an analysis perspective is, how do we distribute loads to the system? So how do we take one of these elements and resolve it into these models? It starts with the loads. I want to talk about loads. And I think that's probably one of the first questions that that we ask as structural engineers is, okay, you've got this beam and you've got this uniformly distributed load, and the load was 2 kips per foot. Well, where the heck did the 2 kips per foot come from, right? You know, if I have a building like this or a bridge, you know, remember, let's go back to one of the topics, even from the RESA discussion. Like, how do you build a model in RESA? You really need 3 pieces of information. You need the geometry, the stiffness, and the loading, right? Now the geometry, and we were talking about, you know, right before the class began, we were talking about clients and architects and whatnot. The geometry comes from the project, right? If you're designing a bridge, the geometry comes from, well, how long does the bridge need to be, right? That's how, you know, how wide is your river? Or how wide is the overpass, or whatever it is that you're crossing. So that's where the geometry come from. Where's the stiffness come from? Well, is it going to be steel? Is it going to be concrete? What's the beam made out of? How deep is it? There's your stiffness. Well, what about the loads? They don't just, you know, appear. You know, we as the structural engineer have to specify them. Okay. Well, let's talk about that. So when we discussed influence lines, we had delineated this difference between dead loads and live loads. And we said that dead loads are basically permanent. They're stationary loads. They're always there. And the live loads are transient. They move. They move around. Well, I want to sort of give you an alternative view of those definitions. That isn't wrong, but it's sort of a different way of looking at it. So in structural engineering context, the primary source of dead load is the structure itself. So if I'm talking about a building, I'm talking about the actual structure. So, you know, we might be talking about the framing, the metal deck that forms up the slab. So here, let's talk about, you know, my office right here. So, you know, this is a steel framed building. So there's the steel frame itself. The floor is a concrete slab. So there's so many inches of concrete. Concrete weighs, you know, we typically assume 150 pounds per cubic foot for normal weight concrete that's reinforced. So however many inches thick the slab is, there's a pressure load. We've got carpet. There's also, you know, this is the second floor of the building. So under here, we've got, you know, the drop ceiling. We've got mechanical and electrical. You know, all of those components that comprise the structure itself, we tend to refer as dead loads. That's not always the only dead load on the structure, but the primary dead load that we as structural engineers need to deal with is the structure's self-weight. It's itself. And the way that we spec that out is typically in terms of pressure loads. So, like, let's take, for instance, the carpet in my office. So my office is carpeted. Each square foot of that carpet, we can determine the weight. Let's say each square foot weighs 1 pound. So, you know, my carpet, I can say weighs 1 pound per square foot. So however many square feet of office space my office has, that's how much the carpet weighs. Same thing with the slab and the framing and so on and so forth. And so dead loads tend to represent more often than not the structure itself and its own self-weight. What about live loads? Live loads tend to represent, the term I tend to use a lot in my design courses is the term occupancy. In other words, what's the structure being used for? So this is, so let's take this. This is a university building. This is a school facility, right? So if you look down here at the bottom, we have schools, okay? So we have classrooms, we have corridors above the first floor, we have first floor corridors. There's also offices in the building. So let's take a look at this. So this office, we would design this floor for a pressure load of, what is that, 50 pounds per square foot. The classrooms, we would design for 40 pounds per square foot. Now look at the corridors. Okay, so notice how the corridors have heavier loads than the classrooms. Why is that? Well, think about what happens in schools when the bell rings. What happens when the bell rings? The hallways fill up, and the hallways tend to have a higher density of people and loading than they do, you know, than the classrooms do. So the hallways see a heavier load. Plus, in emergencies and things like that, they're going to see a lot of loads. So that's why, you know, those are heavy. It's also one of the reasons why the first floor tends to have a heavier corridor load than the remaining floors. Because think the first, let's see. Remember looking at one of these in the Florida Building Code. Yeah, you're gonna and you're gonna find similar entries and tables for different types of structures. Like here's an example. if you look at libraries, libraries have a floor live load of around 150 pounds per square foot. So why are libraries why are structures that are going to be used for a library, why do they have to withstand 150 pounds per square foot, whereas a classroom only has to withstand 40? It's because that structure is being used for a library. It's got to hold up the books. That's what the structure is being used for. And so those book stacks are going to be much heavier than the remaining structure. And we tend to spec out a lot of structural loads like this, not just dead and live. For instance, when you look at your raw snow loads, we have a tool that we can use that, based on our latitude and longitude, we can determine a ground snow load for our location in the country, and then we can convert that to the loads that we would use on the roof, but it's spec'd out in terms of pounds per square foot. Same thing with a lot of other forces. So where does the load come from? Well, it comes from the structure itself, and it depends on what you're using the structure for. And I'll admit, I am glossing over a lot of details that we'll probably talk about in our design courses, like load factoring and live load reduction and some other stuff that'll become important next semester. But for right now, I want you to understand the general concept. Any questions about like the loads itself, how we're speccing them out? Again, we tend to spec them out in terms of pressure, like a pounds per square foot. Any questions on this? All right, so that's great, but how do we take a pressure load like this, something that comes from a Florida building code or from ASC 7 or one of these, spec documents? How do I take a pressure load? Let's say I have an office building, and let's say I'm looking at the offices that are 50 pounds per square foot. How do I take 50 pounds per square foot, and how do I turn it into a simply supported beam? And how do I turn it into a problem that I can analyze as a structural engineer? Well, it begins with the concept of tributary area. So what is tributary area? So the tributary area of a member, and so that member might be a beam, it might be a column, some element in a structure. The tributary area of that element is the area of that floor system or that space that directly contributes to that member. So in other words, it's sort of like what that member is responsible for. And it's best defined as the area that's bounded by the lines halfway next to the adjacent beam or column. And so I'm getting a phone call. I'm going to hang that up because I'm teaching. Okay, we can use this concept to perform what's called a load takedown on a structure, and that's what we're going to do in our example today. And so basically a load takedown is just, okay, here's the structure. Here's a pressure load of 50 pounds per square foot or whatever. How much of that goes to each element that we would then design for? So let me show you. So on this slide, I have a framing plan, and I'm just sort of throwing this out at you, and I want to make sure that this makes sense. So I have a nice little picture here on the board here. So this is a three-dimensional frame, and I kept it simple. I didn't want to make anything too elaborate. I'm also not that good of an artist, so this is about the best you're going to get out of me. And so this would be a three-dimensional representation of a structure that we would ultimately need to design. So I want to name some elements for you so that everybody understands sort of what I'm going to use for a naming schematic. So when I say column, I'm talking about these, I think that's pretty simple. The vertical elements that go from the structure to the ground. What about the flexural elements? Okay, so I'm going to use two terms. Okay, I'm going to use the term beam, and I'm going to use the term girder. Now, admittedly, in structural engineering speak, these two terms are used a bit interchangeably, so they tend to be swapped quite a bit. But if you want me to give you a definition that I like to use, I like to say that the beams frame into the girders. So on this element, or on this structure, what I would say is that this right here, I would say that this is a beam. And if you notice, okay, so here's the beam, and the beam connects to these larger beams right here that then go to the column. So this is the beam, and I would say that this is a girder. Okay, so does that make sense, that idea that the beams frame into the girders? That's kind of the the framework I'm going to use. The other point that I'm going to show you is a lot of times, I mean, this is obviously pretty difficult to draw, at least it is for somebody like me. Do girders typically carry more load? Yes, they do, and that will become very clear here in a second, but you're absolutely right. And the reason why is because of the tributary area and sort of the hip bone connected to the leg bone approach with how this works. Now, what I'm going to do here in a second is I'm going to draw sort of a framing plan for this, and I'm going to be looking, you know, sort of in plan view. So imagine I'm in the helicopter looking down, and so if I'm in the helicopter looking down, what I would see is I would see 1, 2, 3, 4. So these are our columns, right? So, you know, 1, 2, 3, 4, 1, 2, 3, 4. Those are the columns, and then I've got, you know, a girder, and then I guess we can call that a beam, and then 2 beams framing into it. So this would just be a simpler representation of this, okay? All right, and then what I have here in this slide is, you know, that just drawn a little bit bigger for a little bit of a bigger frame. So that's what I mean by the columns, the beams, and the girders, so that you understand what's going on here. Now, like I said, the tributary area is generally defined as the region halfway over to the next adjacent element. So here's sort of what I mean by that. Let's pick a floor beam. Let's take, I don't know, that floor beam right there. It doesn't really matter which one. We just need to pick a random one for discussion purposes. Now, think about this. I've got a floor system. Let's say this floor system has a load of 50 pounds per square foot. How much is this beam responsible for? Well, I need to erase that. I propose that that floor beam is responsible for all, and I'll try and be as clear as I can be. I propose that floor beam is responsible for this area. Okay, and that would be the tributary area for that floor beam. Why is that? Because as soon as I go outside, as soon as I'm like right here, then the other floor beam takes over, right? So that would be the tributary area for this particular floor beam. Now, as Mr. Enoch mentioned in the comment, do girders typically carry more load? Yes, they do. If I were trying to draw the tributary area for, let's say, a girder, let's look at like B2C2. So we're talking about this girder right here, okay? I propose that the tributary area for that girder is going to be halfway over to the next girder, halfway over to the next girder. So that's the tributary area for the girder. So its tributary area is larger. Because it has a larger tributary area, it's going to carry more load. Now, typically the way that we model this is we sort of use like a hip bone connected to the leg bone approach. So let me show you what I mean by that. So here's my framing system here, and let's sort of see if I can draw this isometrically. So let's take the beam indicated. Let's take this beam right here. Okay. So again, this beam has a tributary area halfway over between the two. So its tributary area would sort of be like that. I almost don't want to mess this drawing up, but I'm going to. So that would be that beam's tributary area, right? Now, the way that we're going to handle this is we're going to say, okay, I've got a beam that's experiencing a pressure load of, I don't know, 50 pounds per square foot. Take that pressure load, multiply it by this tributary width, and it's funny how I have a beam, and we'll say that's simply supported, that's experiencing a distributed load. And so that's how I would model that floor beam, okay? And so, you know, here's the length of the beam. I've got this pressure load multiplied by width to get a distributed load. And so I can take this beam and I can determine support reactions. I can, you know, draw a shear diagram, draw a moment diagram, you know, what have you. And another thing to point out is I could just analyze this beam like we've been doing all semester, or I could use what we did on Monday. I could just break out the analysis aids and use those because it's such a simple problem. In fact, you all did this problem for your homework assignment that was due today. Now here's the kicker. This is what I want to ask. Okay, let's talk about the reactions for this beam. Okay, where do those reactions go? Do they just like go straight to the ground? Like, where do they go? Like, how is this beam connected to the structure? The girder takes them, exactly right. They act on the girder. So if I'm looking at this girder, right? So let's say I'm looking at this girder, I might say that this is simply supported, but this girder, instead of modeling it with, let's say, a distributed load, how many beams frame in? 1, 2. So I might say that and that. Now you might go, well, what about these beams? Well, I'd say that this beam and this beam just go straight to the column. So the girder wouldn't see them, but the column would, right? So there you go. So now I've got a model for the beam, and now I've got a model for the girder, and now I can take those problems, analyze them using the methods that we've discussed this semester, and now I've got moments, shears, and deflections, and what have you, that I can start to design based off of. Does that concept kind of make sense? See, I'll show you an example of tributary area in action. So I took this picture, I think about a year or so ago, or maybe a little longer, I don't remember. This is a picture I took of the parking garage. This is the Marshall 3rd Avenue parking garage. So you can see out the little gap there that's the basketball arena. Now, look what's going on here, okay? So each of these are precast double T segments, but we'll just take one at a time. You know, let me see. See, if I look at an individual beam, that's the tributary area for that beam, and then that beam frames into this girder right there. So that girder is going to see a point load from the reaction of each of those beams framing into it. Does that make sense? And this is what I mean by the concept of system loading, a load takedown, and tributary area. Taking a structure, taking a specified load on it, and turning it into a model that we can then begin the process of design. So what I want to do ultimately today is I want to look at an example with tributary area. What I want to do is I want to take a floor system, and I've got a floor system on the next slide. I'm keeping it pretty simple for the discussion today. And I want to take this floor system and turn it into structural models that we can analyze pretty easily based on our techniques that we've discussed this semester. So we have a floor system, and we're going to say it's subjected to a load of 20 pounds per square foot. And so I want to determine some I want to look at a typical interior beam. I want to look at a typical girder, and I want to look at a typical column. And I want to see if we can use this concept to draw out tributary areas and perform our load takedown. So let me stop this share, and let me pull up the I said share. Oh, it's freezing up on me. Give me a sec. If this freezes up on me, my apologies, but my Google Chrome decided just now to not like me very much. Oh no. I'm afraid I'm gonna need to log off and log back on. I really don't like that, but I may have to. Tell you what, I'm gonna close my Chrome and log back in. If you haven't done your surveys, go ahead and do them. Give me a minute or so. I'll be right back. Oh. I think I'm back. I'll just share my entire screen. Okay. All right. So let's see if we can knock out this tributary area problem. Okay. So first thing we need to do is we need to sketch out some tributary areas, and some of these we're directly going to use, and some of them are really just going to be a guide to ensure that we're understanding the process. So first off, we're going to look at an interior beam. So I'll just pick one maybe in this lower left bay, which, by the way, if you notice, the columns are numbered on a grid, and so this is very common in structural drawings that maybe in one direction we'll use letters and another direction we'll use numbers, so that when we're referring to column D4 that we all know what we're talking about. And then the space between the letters and numbers, we tend to call those bays. So if I say I'm going to pick a beam, let's say in the lower left bay, I'm talking about this sort of that region right there. Okay, so let's take a look at this beam. So the tributary area for this beam, we would say, is basically just this, just halfway between. So just curious, what is this width? Just to make sure everybody's paying attention. No. So 50 feet is that entire width there. So where it says 5, yeah, there you go. So yeah, it's 10 feet. Yeah, so if it says 5 at 10 feet, it's saying each of those little spaces are 10 feet. And so the tributary area is halfway over, which is 5 feet on one side, 5 feet on another. So the total width is 10 feet. So let me ask you a question. If we're looking at the beams, can somebody tell me a beam that's going to have a different tributary width or a tributary area? Not the girders, but the beams. Which beam is going to behave differently?
The beams on column line A and D.
Exactly. Yeah, these beams over here are only going to have a tributary width of 5 feet. So here's something to think about. If we're only considering gravity loading, and we're only considering the loads applied, vertically, then the beams on lines A and D would technically only need to be half as big as the ones in the middle, because it's responsible for less load. But that's not always the case in the real world, because sometimes we have additional loads on the outside that we got to consider, like the wall panel. But by and large, it's that philosophy can still apply. What about for the girders? So we said we were going to do girder C2 D2. So girder C2 D2 is going to be like this. So while we're not going to distribute this as a pressure load, this does tell us that the tributary area, that because the tributary area for C2 D2 is larger, that should be a larger structural element. And just so we're all paying attention, what is this dimension here? Oh, I'm telling you. Yeah, it's 30 feet. I'm getting ahead of myself. All right, now for the columns, we're going to look at column B2. Okay, for column B2, what we do is we go halfway over to the next adjacent element. And so when we say the next adjacent element, we're talking about the next adjacent column, right? So halfway over to the next adjacent column would be like maybe over here, or here, or here, or here. So this is the tributary area for the column. So if we're only talking about gravity loading from this pressure load, which of the columns in this building do you think would be the smallest columns? I'm just curious. The corner columns, yeah, the corner columns experience just this little, little tiny bit of load over here, So under gravity load, they are responsible for the least amount of load in the building. It's exactly right. So there you go. So yeah, so these are the tributary areas. So if you wanted to compute, let's say you wanted to compute the tributary area. Let's take the tributary area for, I don't know, the girder. So the tributary area would just be 30 feet times 50 feet. And so that would be 1,500 feet squared. Just as a matter of example. I'm not going to use that value directly, but I kind of wanted to just show you how that works. Now let's talk about actually start using them. And what I tend to do is I tend to sort of work inwards and work my way outwards and sort of use that whole hip bone connected to the leg bone approach. Do you design according to the floor area or some of the tributary areas? What I would say is, you're basically just your role is to design the elements in the system, right? So you take each beam and you go, okay, this is the tributary area for this beam. What beam do I need to use here in order to safely resist those loads? And so by designing all of the beams and all of the columns, you're essentially handling the entire floor area. The two things that you have to watch out for are, one, are you accounting for the entire floor area? In other words, when you do the load takedown, you better make sure that your sum of forces in equal the sum of forces out. That's the first issue. And then the second issue is, when possible, you'd like to repeat structural elements as much as possible. For example, what is really different between this floor beam and that floor beam? I mean, I'm asking, like, is there really anything all that different? I mean, both of those beams are 30 foot long. They both have the same tributary area, and they're both subjected to the same load. So why design each beam differently? Design one beam and just use it all over the place, okay? And so that is sort of the other aspect that we want to try and do, is keep it simple. So use one system and repeat it. Does that make sense? Good deal. So let's look at one of these floor beams, okay? All right, let's take a look at a floor beam. Now, help me out with the floor beam. The tributary width is 10 feet. How long is the floor beam? I just want to make sure everybody's paying attention. I know I already said it, but I'm just making sure everybody's paying attention. 30 feet. There you go. So we know that the tributary width is 10 feet. We know that the length is 30 feet. Now, let's say, for instance, that these are steel beams, just so my image has some, perspective to it. So here's a steel beam, here's a steel beam, here's a steel beam. And so the slab, let's just say the slab, sort of goes on forever, okay? And here's the floor system sort of going out in 3 dimensions. Okay, so that's my quick and dirty 3D drawing. Oh, forgot one. Okay, so just to make sure we're understanding this, conceptually, this dimension is 10 feet. And this dimension is 10 feet. All right. Now, if I'm talking about this beam in the middle, this blue shaded region here, oh, let me get a little better with that. That would represent the tributary width, or the tributary area for a typical interior floor beam, okay? So ultimately what I want to do is I want to take this load here, this would be a pressure load, and I want to convert it into a line load. or a uniformly distributed load, right? So this is 20 pounds per square foot, right? So how do I turn this 20 pounds per square foot into that? Well, I have 20 pounds per square foot applied over a width of 10 feet. So I propose that this line load is going to be, oh, I erased too much, is going to be 20 pounds per square foot times the tributary width of 10 feet, 200 pounds per foot. So in other words, what I have for this floor beam is I have a floor beam that has a length of 30 feet and a line load of 200 pounds per foot. And how did I get that? I took the pressure load and I multiplied it by the tributary width. Okay. The idea is saying, okay, that beam is responsible for 10 foot of that load. So 20 pounds per square foot times 10 foot is 200 pounds per foot. Does that make sense? I want to take a second on that and make sure that's clear. Is everybody good with that? Okay. Okay, good. All right. So here's the beauty of this. Okay, take a look at this. Does that problem look familiar? It should. You just did this on your homework on Monday, right? So, or that was due today. So we can say that the reaction equals shear max equals what? WL over 2, right? We can say that M max equals what? What's the maximum moment for this beam?
WL squared over 8.
There you go, WL squared over 8. So now we can start designing, right? We know the maximum deflection, we know the maximum shear. You know, we can begin our process of design. And while we're at it, let's go ahead and compute a couple of these. So this is 200 pounds per foot times 30 foot over 2. 200 pounds per foot, 30 foot squared over 8. Let me move this up so it's out of the way. Okay, so 200 times 30 over 2 is 200 times 15. So what's that, 3,000 pounds? Or 3 kips. All right, and 200 times 30 times 30 over 8 is 22,500. And this is a moment, all right? And so the units are going to be foot pounds, or 22.5 foot kips. And so that's what I would design that beam for. I'd make sure it can hold up a maximum shear of 3 kips and a maximum moment of 22.5 foot kips. Now, that's not the only thing I would design it for, but that's what next semester's for, because we got serviceability limits and all sorts of other stuff to consider. But does that make sense? Now, check this out. Let's look at the girders. Okay, now I'm going to cheat. I'm going to copy this. Okay, so let's look at the girders. Okay, and specifically, we're looking at, I think it was C2, C3, or no, C2, C3. It's C2, D2. What? C2, C3 is just a beam. C2, D2. So help me out. How long is C2, D2? Just make sure everybody's paying attention. No, not 10 foot. That's 50 foot. Yeah, here, maybe it's small. That might be on me. Yeah, so we're talking about this element right here. And so that's that 50 foot right there. All right, so its length is 50 foot. Okay. Now, let's say we have a beam, an analysis model of a beam that's simply supported and it's 50 foot long. Now, this is a girder. We typically model girders with concentrated loads. Okay, and so I propose that this is going to have 1, 2, 3, 4. 4 concentrated loads. All right, and that's going to be, each of those are going to be spaced 10 foot apart. Now, I'm curious if anybody can tell me how much are those concentrated loads going to be? Like, I got a concentrated load. What is that? Okay, all right. So are you saying then that, sorry, 3 kips? Because that's what we got up here, right? Well, the beam that frame into it, we use WL/2 and we got 3 kips. So my question is it 3 kips? Here's what I'm getting at, okay? No, no, you're fine. You're completely fine. Here's my point, okay? Let's take a look at this floor beam. So here's the floor beam, right? So what I'm saying is I've got, here's this, there's the floor beam, and I've got 1, 2, 3, 4. But let's take a look at the framing plan, okay? What's happening like right here, okay? How many floor beams are framing into the girder right there? Is it 1 floor beam or is it 2? It's 2, right? So here's my point. When we looked at an individual floor beam had a reaction of 3 kips on either end, but there's not 1 floor beam framing in, there's 2. There's 1 up top and 1 on the bottom. So I propose that these point loads are not going to be 3 kips. They're going to be 6 kips. Because there's, the contribution from this floor beam, but then there's the contribution from that floor beam. And so each one has a 3 kip load on either side. So that girder has got to be responsible to hold up the floor beams from either end. Does that make sense? Yes, exactly right. You're exactly right, because C1D1 only has 1 set of beams framing into it. So just like before, when I asked, like, what's the deal, like which of the floor beams are going to be smaller, and we said that the floor beams on the left and right are going to be smaller because they have less tributary area. The girders on the top and bottom are going to be smaller because they are responsible for less tributary area themselves. And this is how we would represent that. Exactly right. You're exactly right. Now, just to make sure everybody's paying attention, and I want to show you something pretty slick. Can somebody tell me what the reactions are going to be for these girders? I didn't hear anything. Somebody turned the mic on and then.
It's going to be 12 kips apiece.
There you go. All right, perfect. Now I want to show you something pretty slick. Okay, so 12 kips. Now watch this. Okay. Now, somebody help me out. Let's look at one of these columns because I know we're running out of time, but I want to knock this one out because I think this is pretty slick. All right, let's take one of the columns. Can somebody tell me what is the tributary area of column B2?
$750.
Hold on now. So here's the tributary area. This dimension is going to be 30 feet. This dimension is going to be 25 and 25, 50. Right? So is it 750?
No, it's 1500.
Yeah. So it would, yeah, 1500. Yeah, it would be 750 if we were looking at like B1. All right. Now check this out. The original pressure load was 20 pounds per square foot. So if I wanted to determine the load on column B2, I could say 20 PSF times 1,500 square feet, and 20 PSF times 1,500 square feet is what, 30,000 pounds? Or 30 kips? Would that be a fair statement?
Sure.
Now, here's the other slick part, okay? Let's look at this from a framing perspective. If I look at column B2, okay, column B2 has two beams framing into it, and it has two girders framing into it. So check this out. The reaction from the beams was 3 kips, and the reaction from the girders was 12 kips. Well, if there's 2 beams and 2 girders, 2 times 3 plus 2 times 12, 30 kips. Bam, bam. Physics. It's awesome.
So this is going to have to be your chunkiest column.
Yeah, and think of just the magnitude of these loads. I mean, this framing plan is not outside the realm of reality, but look at what's going on here. 20 pounds per square foot. 20 pounds per square foot. So a square foot has 20 pounds on it, and that causes 30 kips on a single column just for one floor. Like, imagine if this was a 10-story building. Like, these loads can get amped up real quick, you know, and think 20 pounds per square foot didn't even show up on that table on the slide, right? We were talking about hallways with 100 pounds per square foot. We were talking about libraries with 150. The loads in structural engineering land get real high real quick. So it gives you a little bit of an understanding of like the bigger picture, because, you know, like what we do, I mean, if we screw up, that's a lot of force that can cause a lot of damage. But I just think this is kind of slick how in the end it all balances out, you know, depending upon how you look at it. Any questions before we call it?
It kind of puts into perspective how like one PT cable handles 27 kips of force, one cable.
Well, and the to give you some numbers, regular old everyday structural steel, A992 grade steel, has a yield strength of 50 KSI and a tensile strength of 65 KSI. Some pre-stressing strands have an ultimate tensile strength of like 270 KSI. It's crazy how much force they can withstand. They experience a significant amount of load. But yeah, ultimately the idea is now you can take a real life structure and turn it into this. And like we've been doing these all semester, like if you could do some of the problems we did earlier on, you can certainly handle this. Like that's the whole point, is now it sort of ties everything together. All right, we are definitely out of time. The slides for the exam review are up. I would take a look at them and come prepared with questions on Friday, everybody. That's all I have. I will see you all then. Y'all have a wonderful day. That's kind of the hope, is that in the, like, you know, we do a lot of these models, but ultimately we want to take it back to real life. You know, that's what I'm hoping to do. And next semester is definitely real world territory in steel design. So if you're interested in furthering that, that's a great class to take. That's all I have, everybody.